Okay, let's wrap up chapter 2. So last week we covered the second half of chapter 2, which discussed displays for categorical data. And what do we call those things? Bar charts. Okay, so for categorical data, okay, we can display with bar charts, okay, and pie charts, but we prefer bar charts. Let me just get this in here. Okay, and so today we'll talk about numeric data and how to display numeric data. Okay, and so we have a few displays, and first we'll talk about dot plots. Then we'll talk about histograms. Okay, the book mentions stem plots, but I will not cover that in class. Okay, so stem plots will just be, are covered in the book. Okay, and then later on, this is more so looking forward to chapter 3, we'll have box plots, also called box and whisker plots. Okay. And so whenever we have a graphic display, you have to think, what is this thing trying to convey? And so our graphic displays for numeric data are trying to display in a succinct manner the contents of our data. Okay, so whenever you have some kind of data set, you have rows and columns, right? What do the rows represent? Okay, rows represent each observation, or each person, each person, etc. And what do the columns represent? The columns represent the variables, okay? And you might have numeric variables or you might have categorical variables, okay? Okay, and so when we're talking about displaying numeric data, we're saying we've got some kind of data set with lots of rows, okay? And perhaps multiple columns, maybe only one column. And all we're doing, so maybe we have rows, we've got the name of someone, we have Adam and Bob and Carol and Diane or whatever, okay, etc., etc., etc. Okay, and maybe one of these is age, okay, or and here we're just talking about one column, which is numeric. Okay, so we are trying to summarize. We are summarizing a single numeric column of data. Okay, and we're going to do it with a dot plot and a histogram, just to get us started here. Okay, and so so we could pretend that we're just if we just look at this one column, which contains age, okay. Looking at that one column only, perhaps the numbers we see are 20, 25, 36, 18, 52, something like this, okay? and we can have lots and lots of data points. All right. Well, we can put, if these are the 1, 2, 3, 4, 5 data points, let me copy them onto the next slide here. Just want to, some of you guys are still writing, so I'll give you a moment to catch up. Yes, question? Do we have light control? If so, is it possible to have first row? Yeah, let me see what I can do here. Okay. Is that awesome? Thank you. Better? Okay. All right. Okay. So just again, we're just taking a look at that one column in the data set, which is our column of ages, and we can plot this on what we call a dot plot. Okay. And what a dot plot looks like is we've got a number line. Okay. Maybe I'll start it at 10, 20, and I'm kind of, I guess I have the capability to excuse me. Thank you. So this is 15, 16, 17, 18, 19. Oh. All right, and this is, this is not a perfect scale here, but I can kind of copy these. So that goes to 30, that goes to 40, 50, and 60 here. Okay. So and all we do with the dot plot is, so you first need a number line. Okay, so you first, the dot plot always requires a number line. Okay, and then what we do is we place dots at the location of each data point. Okay, so we're going to say here's a dot at 20. We place a dot at 25. We place a dot at 36. Here's a dot at 18. And here's a dot at 52. Okay, so each value in our column of data gets a dot in the dot plot. Okay, and that's essentially what a dot plot is. Now, depending on the data, you could end up getting a dot plot with lots of dots. Okay, and it might. So I'm just kind of drawing a bunch of stuff. Okay, and you could have a dot plot that looks something like this. Okay, so this is just an example of a dot plot with more data. Okay, and so depending on the size of your data set, you're going, well, for all dot plots, you should have one dot for each data point. Okay. So one dot for each data point. And so, you know, if you have a very large data set, say, you know, 10,000 data points, you're going to have 10,000 dots, and that might be a little bit cumbersome to display. We might not want to do that. You know, I would say it's great if you've got, say, 100 data points or less. You know, maybe even 200 is okay, but you know, once you get beyond that, then you're starting to get way too many dots. So I would say if your data set has 100 data points or less, a dot plot is probably fine. But much more than that, your dot plot probably too many dots and not a whole lot of fun to see. You know, and to manually draw a dot plot, you can imagine that becoming quite tedious if you've got a lot of data points as well. But you know, you can compare dot plots one group to another just by kind of seeing where the location of the dots are, and you know, even in just this data set with 5 data points, you know, we see some slight trends, meaning that, you know, kind of there's a higher concentration of ages down here, and then up here it's a little bit more spread out. Okay, so you can even see that with just a few dots. Okay, so this concept of our idea of having way too many dots to display leads naturally to a histogram. Okay, and a histogram is like the dot plot, but instead of dots, you have bars. Okay. Okay, and so you know, a histogram might end up looking something might look something like this. Okay, and then of course, just like the dot plot, along the bottom we have some kind of number line. Okay, and so this, I'm just making up arbitrary numbers here. Okay, and so with a histogram, the horizontal axis is a number line. Okay, the height of each bar represents how common or frequent that value appears. Okay, and so here the width of each bar is 2 units, and so our tallest bar is this one right here. And what that tells us is that the most common values, most frequently or frequent values in our data set are 30 and 31. Okay, And the next most common, or next most frequent values, are 32 and 33, followed by 28 and 29. Okay, can we see that? That the tallest bar represents the most frequent, and so that's going to be kind of 30, 31. And then the next tallest bars is this one and this one. And so so the next most common values would be 18, 19, 32, 33, things like that. I mean, not 18, 28, 29. And then and we see we don't have any values at like 44. We do have maybe one or two values at 46, or however tall the height of the bar. Sometimes, or a lot of times, you'll have a kind of a vertical axis kind of giving you an idea of exactly this height represents, who knows, maybe this height represents 10 appearances and this height represents 5 appearances, or whatever it might be. Okay, you might have some kind of scale on the vertical axis. Maybe, maybe not. Okay. The scale on the vertical axis is not required. To tell you the exact frequency. Okay, but not required in the histogram. The horizontal axis should have numbers on it though. Okay, that's almost always required, at least in regular graphs. Maybe in a homework problem where they're trying to get you to think about the data or something, maybe they hide the numbers from you. But in general, you need to have numbers on the horizontal axis. Okay, and so this is a histogram, and in our example, each bar represented 2 values, but depending on the data that you have, you could have each bar represent just 1 value, or it could represent 100 values or something. If you're gonna, or even you might have histograms to represent someone's people's incomes. Okay, now if we looked at your IRS tax forms, it's very unlikely for 2 people to have the exact same income. Okay, to the nearest dollar. Okay, you might have a few people with the exact same income to the nearest dollar, but most likely people's incomes will vary quite a bit, and it might make sense to group people in income, having a bar represent maybe like a range of $5,000 or something like that, and say these are people who made between 50 and 55,000, or 50,000 and 54,999, and this is 55,000 to 59,999 and 60,000, and so on and so forth. And you have kind of these divisions of $5,000 increments at a time. So depending on the data that you have, I'll write this. Okay, you may choose to have each bar in the histogram span 1 value or many values. Okay, so something like if we asked how many children do you have, probably it makes sense to have each bar represents one value, right? Because it'd be like people are gonna either answer I have 0 kids, 1 kid, 2 kids, 3 kids, 4 kids. You know, I mean, you might have some people who respond with something like 12 kids or something, but even then, you're not gonna have more than 12, 15 bars or something like that. Okay, so you don't have to worry about having way too many bars, just because as far as number of kids go, the range goes from 0 to some 2-digit number. Okay, unless somebody just adopted hundreds of kids or something, whereas something like income, you're going to have a huge range of values, and so it makes sense to have each bar kind of span thousands of a range of $1,000 or $5,000 or something like that. Okay, so this could be an example. And over here, annual income's all right. Yeah, we'll just write income. Okay, and so that's a histogram, and maybe just a quick check. What kind of data are we summarizing with a histogram? Numeric data. Okay, so those of you who said categorical data, I don't know, I'm grumbling. We are displaying numeric data with a histogram, and so when you see a bar, what this says is that there are 10 people who have whatever we're talking about, 30 something. Okay, so maybe maybe this is we're asking what size, I don't know, whatever. I was gonna say like what size waist, but I don't know if anybody has a 20-inch waist or something, so it doesn't quite work. But what size is something, 30, 31, these are probably the most common for whatever we're talking about here. Okay. So keep in mind, histograms are for numeric data, and we can kind of, we can summarize the shape of a histogram with kind of this curve. Okay, so rather than having to draw every single bar, something like this, we can kind of say, and I'm just something like this. So we can say this represents this. Okay, so this curve kind of represents this, and what exactly does it mean to have a shape like this? Okay, so what does it mean for your numeric data to have this shape? Okay, so well, what are the most common values that appear? Okay, I don't have the number line labeled, so how would you kind of describe where the most common values are? Huh? Okay, but where is that located in terms of the values that we have? Are they, are the most common values values high in the spectrum, values low in the spectrum, values in the middle of the spectrum? In the middle, right? Okay, so the peak representing our most common is in the middle. Okay, so the middle is most common. Okay, so, and whereas down here, low values are less common, low values are uncommon, and high values are uncommon. Okay, so this could be something like height, human height. If we were to look at just one gender, most people are average height. Okay, so if we're talking about men in the United States, that's around 5'9", 5'10". Most men are somewhere around there. Sure, you have people who are taller than that and people who are shorter than that, okay? But, you know, if you go way above that, say 6 inches above 5'10", to say something like 6'4", that's going to be less common. And if we went 12 inches above 5'10" to 6'10", that would be very uncommon for a height, okay? And if we went the other direction, okay, 6 inches below 5'10", that would take us down to around 5'4", 5'3", 5'4", okay? That's that would be uncommon for the height of an adult male, okay? Of course, there are men with that height. And then if we went a full foot below 5'9", 5'10", that would take us to 4'9" and 4'10", and that would be quite uncommon for the height of an adult male. And so what does it mean for your numeric data to have this shape? This shape is symmetric and unimodal. There's two words that we use to describe it. Okay, symmetric meaning kind of yeah, I guess what happens on the low end is happening at the high end, okay? So in this case, low values are uncommon. And so symmetric means that if the low values are uncommon, then the high values are also uncommon. Okay. Unimodal, that means one peak. Okay, so there's one set of values. In our case, the peak is in the middle. In the middle, so that means values in the middle are more common. Okay, so examples of this: human height for each gender, IQ scores. Okay, IQ scores are unimodal and symmetric. Okay, most people have IQs around 100, maybe a little higher, maybe a little lower, but most people are around there. And then you have some people who have very high IQs of like 130, which is quite high. And then and about the number of people you have with IQs of 130, you're going to have about the same number of people who have IQs of around 70. Okay, so 130 would be 30 points above the average of 100. You're going to have about that many people with IQs of 70, which are 30 points below average. Okay, and then as you go further out to say some, very extreme IQ scores like 150, which is really high. You're not going to have very many people, so that's quite rare, as well as scores of IQs of 50 is also quite rare in how common or uncommon things are. So whereas the vast majority are going to be between 90 and 110 or something like that, okay? Or maybe not the vast majority, but quite a few. So so we call this unimodal and symmetric. This is also known as kind of the bell curve. But we call this unimodal and symmetric. Okay, so I'll say unimodal, meaning one peak, and symmetric. And again, this represents, keep in mind, always we're talking about numeric data. So, if we're talking, if you have categorical data, it doesn't work, okay? Categorical data, if we're talking about hair color, or the color of your car, or, which brand cell phone you use, it doesn't make sense to talk about a bell curve, okay, or things like that. Data can come in other shapes, okay? So we can have something like this. Let me kind of draw this. So this also has one peak, so we would say this is unimodal. But this is skewed right, okay? The shape here is skewed right. So what does it mean for your data to be skewed right? What values are most common? Okay, so kind of values kind of in this lower end are most common. So the middle of our, or the central values, okay? This idea of central values are on the lower end of the kind of the spectrum. Okay, so kind of, this is the quote unquote middle of our data. Okay, it's not the middle of the range, but it's the middle of our data, if that makes sense, okay? So this is the middle. When I talk about this, it's the middle of the data, not the middle of the range, okay? Okay, and this is, these values, in this vicinity, these are kind of our most common. This is the range of, most common values. Okay, and what we have going on here is we've got values that are way higher. Okay, very high values exist. Not a whole lot of them. But we do have values that are way higher than typical or what the middle is, okay? So we have some values that are much higher than the rest, okay? Do we have values that much lower than the rest? Than the middle? No, okay? So if we look out, we're, this far above the middle. If we went that way, it's not on the chart, no one down here, okay? Maybe I'll use it in red. No one exists down here, okay? So can we think of something that might be skewed right? Some data that might be skewed right. Okay, well, I'll give you an example. Remember, we're talking about numeric data here. So income levels. Okay, so income levels are skewed right. So, in the United States, probably most people probably make between $30,000 and $100,000 per year. Okay, so most people make somewhere around there, between 30 and 100,000 a year, and that would kind of span our middle range of values here. Okay, and let's just say the average is, just for simplicity's sake, let's say the middle is 50,000. Okay, just for simplicity. Do we have people making $1 million a year? Yeah, okay, not a whole lot, but we do. We do have people who make $1 million a year. $1 million a year is 950,000 more than $50,000 a year. Okay, if our average is 50,000, $1 million a year is 950,000 more. Okay, so that would be way up here. What does it mean to make 950,000 less than average? That would mean your wage is negative $900,000 a year. Okay, does anyone have a wage of negative $900,000 a year? No, it's not possible. It's not legal to pay someone a negative wage. I mean, you have stories of like CEOs taking a salary of $1 for the year or something. But in general, you cannot pay someone a negative wage. So you're going to have no one below $0 a year, and so as far as income levels go, it is skewed right. Okay, so just kind of to recap, we can say average maybe 50,000 per year. Okay, some people make 1 million per year, okay, which is 950,000 more than average. Okay, no one makes 950,000 less than average. Okay, in fact, okay, it is not possible to make less than 0. Okay, and so as far as, if you think of the grand range of incomes, okay, 50,000, which is not that low of a value, but comparatively to $1 million, 50,000 would be on the low end, and so that's what we have going on in this picture. The middle, the average income or whatever, is comparatively low on the low end of the spectrum when you're taking into account the entire range of possible values. Okay, does that make sense? Income being right skewed. Okay, so that's what it means to be right skewed. Can I flip to the next slide, or are you guys still writing? Okay, looks. Okay, and on the other side we have this. What do you think this means? Left skewed. Okay, so this would be left skewed, and this is also unimodal. Okay, so same concept, just flip it around. Okay, you got values much lower. The quote middle is on the upper end of the spectrum, whatever that might be. Okay, so this could be, an example would be test scores on a relatively easy test. So, maybe your average score is like 85% or 90% or something like that, okay? So, on a regular test, you can't get over 100%, so your maximum is capped at 100. But, whenever you give a test, you always have somebody who scores, 20% or 30% or something like that. So you're going to have some people, at the lower end, but not a whole lot. But as far as you know, comparing where the average is and where the max is, you know, the averages might be closer to the maximum scores, okay? So that would be left-skewed unimodal. And then we have data that looks like this. This is bimodal, okay? And this means there's two peaks, okay? And this is a very exaggerated situation of bimodal. This also counts as bimodal, all right? You know, these are also bimodal. And so what might be bimodal? Okay, so as far as bimodal goes, we're still talking about numeric data. All right, so you know, if you're thinking of categorical things, those will not work as bimodal. Okay, so we can think of a lot of, you know, we have dichotomies, you know, at least for, like, you know, in politics we have, you know, kind of liberal and conservative political ideology, but that's categorical, okay? So so that would not count as something like this. Yeah.
Could you use weather?
Weather, okay. What are you thinking for weather?
I don't know, like maybe different temperatures in different, like, times of the year.
Okay, so you know, I would argue that weather, you probably won't have an extreme dip in here, where, you know, probably most common temperature is around 70-ish degrees. The average temperature of whatever it might be, 60-something degrees. But yeah.
Can you use pole numbers?
Huh?
Pole numbers?
Pole numbers? Okay, so a lot of you guys are thinking of kind of like time series things where things go up and things go down. But that's not what we're talking about here, okay? So you guys are, a lot of you thinking, yeah, time series situations where we have things going up and down. No, we're talking about a single, you have to imagine a single column in your data set, something like age or something like, you know, the number of kids or whatever it might be. We're looking at one column, and yet are there something where we're going to get two central peaks for something like this? So I'll give you an example, okay? If somehow we got into your medical records or something, and probably people don't even have this number in their medical records, but we could measure people's testosterone levels, okay? Everybody produces testosterone in their body, but in general, men produce much more testosterone than women. But if you looked at all the men, you would have some men producing more testosterone and other men producing less testosterone, okay? And this is more so, testosterone is more related to your personality than your appearance, okay? And then as far as women go, women produce testosterone. Some women produce more testosterone than others, and some women produce less testosterone than others. But what you're going to see is that, you know, this might be the, quote, average male testosterone. Level, okay? And this would be a numeric thing. You spit in a cup and you get some kind of measurement. It's like your testosterone level is this number, whatever that is, okay? And then and over here, this might be your average female testosterone level, okay? Okay, and so this, someone up here, this would be you know, a man with high testosterone. Okay, someone right here would be kind of your average male testosterone. Okay, and then someone over here, this could be either a man with low testosterone or a woman with very high testosterone, right? Okay, so this is either, you know, man with low or woman with high. Okay? And then down over here, this is most likely a woman with low testosterone. Okay? And, I don't know if the difference would be this pronounced, or maybe it's more pronounced or less pronounced. I don't know. I don't know these things, but we would see some kind of two-peak formation where you would have kind of your average testosterone levels for women and average testosterone levels for men, and some kind of variation around those things. Okay, so again, you have to think. We've got one column of data that we're looking at in our entire data set. Will we still see, different peaks in our data here? Okay. Okay, let's. So that covers basically what I wanted to wrap up in chapter 2. Why don't we take a 10-minute break, and then we'll delve into chapter 3 in earnest here.